So last day we were looking at a couple of things. We started out looking at an asteroid impact, and we said even a fairly small asteroid of a few thousand kilograms, starting from not that high up, basically had about the same the same energy impact as a small atomic bomb, and they get bigger and they get larger. And I hopefully went on a rant with you where I said, as you become adults, just pay attention to that in your voting and the way we allocate our taxes. We tend, you may notice based on our response to COVID, to not be very forward thinking. We react rather than proact, and I would rather be proactive. Talked about geosynchronous satellites, but then we started going to black holes. So we looked at the gravitational field strength near a black hole, talked about escape velocity from a black hole, and we said there's a term for what happens when you fall into a black hole. It's called spaghettification. And then I think I went on a long rant about the first photo of a black hole and how it was actually way cooler than you realized. You're actually seeing the back of it with the light curling over on its way away from you, getting warped and bent, and you were actually seeing the back side of the black hole, not the front of it. Some really neat stuff going on there. Example 4, a black hole has a mass of that. Suppose a spaceship is that far from the center of the black hole. What's the gravitational field strength? Again, the most common mistake I see is kids go, oh, gravitational field starts with the letter F, and so they find this. What have they found? Gravitational field? Force, which I know begins with F. By the way, the reason I keep harping that is our next unit is going to be electrostatics. We're going to have electric force and electric field. And again, kids are going to get tempted to mix them up. So we really got to pay attention here. How do I find gravitational field? It's the force at that location divided by the mass at that location. It's the obvious one, get the little g by itself. Except since we're cosmic, we have to use big G, big M, little m, over r squared over m. And this is where we get gravitational field strength, which is what I started this unit with, is that. This is what Isaac Newton showed, that gravitational field strength depended on the mass of the object creating the gravitational field and how far you were from the center, squared. Oh, and then we said he couldn't find big G. He knew it existed, but it was too small. Cavendish came up with a clever experiment. All right, well, let's plug in our numbers. It's going to be big G. Looks like the mass of this black hole is 7.21 times 10 to the 31 divided by... Now, Mr. Dewick, I don't think I would get force mixed up because there's big M, but I don't see little m. Hey, I bet you on the test I'll also tell you the mass of the spaceship just to tempt you. Yeah. 9.6 times 10 to the 9th squared in this way. Yeah. Where isn't it squared? Energy. It's going to be big G, mass of the black hole, divided by 9.6 times 10 to the 9th squared. I have a feeling this is going to be a fairly strong gravitational field. 52.1? Is that right? About 5 Gs-ish. B asks, what's the escape velocity? Again, we derive it from conservation of energy. If you're looking for a bit of a shortcut, what we're really saying is this. All of your kinetic energy from the rocket has to be turned into potential energy. Well, no, that's not quite what's happening. It's your initial kinetic and your initial potential have to be the same, so you end up with no energy. It's a little bit weird. It's this weird system. You're going to have a half little m v squared equals big G, big M, little m over r. I should have put a negative here because you get a minus minus, which is a plus. I didn't derive that very well. The little m canceled. We derived it on the previous question, I think, a lot better. or here. Where's the, we did an escape velocity somewhere here, didn't we? There it is. We derived it better in part C on the previous question. So we end up with escape velocity is equal to the square root of 2 big G big M over R. I'm looking at my calculator. I notice right now I have big G big M over R. I think if I backspace a little bit, insert a 2 times in the front, and get rid of the squared, that should work. Oh, and then square root of that. And I get 1.00 times 10 to the 6th. Is that right? 1,000,000 meters per second. If you were closer, is that right, George, or am I wrong? I have no idea what you said. I have no idea what that was either. So just. Oh, you think your answer is wrong? Am I right? Yeah. Then your answer is wrong. Yeah. You can replace the word think with "I'm absolutely certain that." Just say it. Okay. Yeah. Good. Pause. So, if you moved closer, would escape velocity be bigger, smaller, or stay the same? Well, as this number gets smaller, as R gets smaller, what happens to this answer? Bigger. That leads us to this concept called the event horizon. What's the event horizon, or the Schwarzschild radius? That is when v escape equals the speed of light. So what we're going to do, Zach, is we're going to start with escape speed. V escape equals the square root of 2 big G big M over R. We're going to get the R by itself, and then we're going to replace for V the speed of light, which is 3 times 10 to the 8th. Zach, where is the R right now? Inside the square root? You know what? I'm going to square both sides. That'll get rid of the square root on the left, and I'll end up with this. V squared equals 2 big G big M over R. Now stuff moves diagonally. R, which is the event horizon radius, or the Schwarzschild radius, another name for it, is equal to 2 big G big M over V squared. If I plug in my numbers, it's going to be 2 big G mud, what's M? What's the mass of the sun, by the way? Something 10 to the 30th, 10 to the 31st, so roughly 10 times larger, heavier than the sun, okay? Divided by, and then to find the event horizon, the speed of light. Oh, and in this case, it's squared. If we wanted to define the size of this black hole, and it's a little awkward to talk about sizes of black holes, so we use terms like Schwarzschild radius or event horizon. You saw from the video we watched yesterday that a black hole is way more complicated than you realize, but cooler. Where is the point of no return for anything in our universe? Sarah, what'd you get? Oh, still typing? Busted. Sorry. I thought you were done. 2 times 6.67 times 10 to the negative 11 times 7.2 times 10 to the 31 divided by 3 times 10 to the 8th squared. Look for typos. That looks good. Do y'all get 106,720? Nice that it works out fairly evenly. 1.07 times 10 to the 5th. Meters. Or if you were creating a black hole, Taryn, and you had 7.2 times 10 to the 31 kilograms of hydrogen and helium, you would have to compress that star, shrink that star down until it was smaller than that, and only then would you have created an event horizon. Okay? Let's destroy our solar system. Suppose the sun began to collapse for some strange reason, and it maintained its mass, but its radius began to decrease. At what radius will it become a black hole? This is called the Schwarzschild Radius. This is also where the event horizon begins. So, Braden, it's going to be the same approach. We start out with escape velocity. And we get the R by itself, which I'm pretty sure was R ended up being 2 big G big M over V squared. You know what? If I just backspace and edit on my calculator, I think I can just replace the mass of the black hole with 5.98 times 10 to the... No. So what was the mass of the sun? I'm sorry. I'm doing the mass of the Earth. We'll call it hole in the mud. What was the mass of the sun? 1.98 times 10 to the... That should work. Yep. Just under 3,000 kilometers. Meters. Sorry, meters. Kilometers? Meters. Is that right? Yeah. So, really... about the size of downtown Pitt Meadows. Roughly, it has a 3-kilometer radius, 6-kilometer diameter. Is that all right? What's your homework? The ultimate review. But first, put your pencil down, please.